What is the Silicon Controlled Rectifier, SCR? A powerful electronic switch. Today, we are going to dive into a fascinating and incredibly useful electronic component, the Silicon Controlled Rectifier, or SCR. Often referred to as a powerful electronic switch, the SCR plays a crucial role in many power control applications, and by the end of this presentation, you'll have a solid understanding of how it works. What is an SCR? So, what exactly is an SCR? At its core, an SCR is a four-layer semiconductor device. Think of it as a sophisticated electronic switch. Its primary function is to control the flow of current between its two main terminals, the anode and the cathode. You might also hear it called a solid-state thyratron, which gives you a hint about its operational similarities to older vacuum tube technology, but with all the advantages of modern solid-state electronics. How does it work? Overview. The fundamental principle behind the SCR's operation is quite elegant. Unlike a simple mechanical switch, an SCR can be turned on and off by applying a small electrical signal to a dedicated control terminal, called the gate. The truly unique aspect is that once the SCR is triggered and turns on, it remains in that conducting state, even if the gate signal is removed. It will only turn off when the current flowing through it drops below a certain threshold. Internal structure, the PNP stack. To understand how it achieves this, let's look at its internal structure. The SCR is formed by alternating layers of P-type and N-type semiconductor materials, creating a PNP structure. This specific arrangement of layers is key to its switching behavior and its ability to latch on once activated. The three essential terminals. Every SCR has three distinct terminals, each serving a specific purpose. We have the anode, which is typically where the current enters the device. Then there's the cathode, where the current exits. And finally, and most importantly for control, we have the gate terminal. The gate is the control input that allows us to switch the SCR between its on and off states. Initial state, the blocking mode. Let's start with its initial state. When no gate signal is applied and the voltage is in the correct polarity, the SCR is in what we call the forward blocking mode. In this mode, the SCR acts like an open switch, effectively blocking the flow of current from the anode to the cathode. It's ready to be turned on, but it's not conducting yet. Activating the SCR, gate triggering. To turn the SCR on, we use the gate. When a small, positive current pulse is applied to the gate terminal, it triggers the SCR. This small gate current initiates a chain reaction within the semiconductor layers, causing the SCR to rapidly switch from its blocking state to its conducting state. It's like flipping a very sensitive electronic switch. The activated state, forward conduction. Once triggered by the gate, the SCR enters the forward conduction mode, which is its on state. In this mode, current flows freely from the anode to the cathode with very little resistance. A critical characteristic here is latching. Once the SCR is on, it stays on, even if we remove the gate signal. It will continue to conduct as long as the current flowing through it remains above a certain minimum value, known as the latching current. Deactivating the SCR, turning it off. So, how do we turn an SCR off if the gate signal no longer controls it directly once it's latched? The key is to reduce the anode current. If the current flowing from anode to cathode drops below a specific value called the holding current, the SCR will automatically turn off and return to its forward blocking state. The holding current is typically a bit lower than the latching current. This characteristic makes SCRs ideal for AC applications, where the current naturally drops to zero every half cycle. Important features of SCRs. Let's summarize some of the SCR's defining characteristics. First, it exhibits one-way conduction. Current can only flow from anode to cathode when the SCR is on. It does not conduct in the reverse direction. Second, and as we have emphasized, there's latching. Once triggered, it remains on until the anode current falls below the holding current. And finally, SCRs are known for their high efficiency. They can control very large currents with only a small, brief gate signal, making them excellent power switching devices. Where are SCRs used? Given these unique characteristics, SCRs are found in a wide array of applications. They are essential in rectifiers for converting AC to DC power, especially in high-power scenarios. They are used in inverters to convert DC to AC. You'll find them in motor control systems for adjusting speed and direction, and extensively in AC power control circuits for things like light dimmers, temperature controllers, and regulated power supplies. Their robustness makes them ideal for industrial and heavy-duty applications. Summary. In conclusion, the Silicon Controlled Rectifier is a remarkably versatile and robust electronic switch. Its ability to be triggered on by a small gate signal and then latch into conduction until the current drops below a holding threshold makes it indispensable for managing and controlling significant amounts of power. It's a fundamental component in modern electronics, especially in power electronics. Thank you for your attention, and I'm now happy to take any questions you might have.